Have you ever wished to experience magic in its purest form? To be in many places at the same time? Or to be able to predict the motion of an object thousands of kilometers apart? Well, my friend, I have good news, because sometimes magic equals physics. Quantum physics, to be exact. What? You don't believe me? Well, I'm not crazy, and to prove it, I invite you to come with me and discover the fascinating phenomenon of quantum entanglement. Quantum entanglement happens in a world within our world, in the microscopic universe where reality fuses with fiction. But what is it? Let's start with an analogy. Well, imagine that you have a pair of smelly shoes, and because of their terrible odor, you put them in two separate but identical boxes. You then mix them up until you are unable to distinguish which box contains which pair. Then you give me one and take the other box home. When you arrive to your house, you proceed to open it and notice that the left shoe is in it. If this is the case, which shoe do you think I will see? Correct, it's the right one. As soon as you open one box, you know with complete certainty what I will see, even though you have not yourself looked into my box. It is also important that you notice that no matter how far we are from each other, the correlation will not change. If you happen to find the left shoe, you know that I will have the right one, and vice versa. This simple example can help you understand what quantum entanglement is. However, the analogy is not completely accurate. This is because in it we are talking about classical correlation, but quantum entanglement is quantum correlation, which is much more exciting. In quantum mechanics, we say that when two particles interact physically with each other, they become entangled. This means that their properties become somehow connected. Measuring a state of one particle will tell you the state of the other one, with 100% certainty. This perfect correlation works in a similar way to how you knew which shoe I would find when I opened the box. However, here is where the analogy becomes faulty. In the shoe example, the information was there all along. The left shoe was always inside the box you took, and the right one was always in the box I had, whether or not someone looked at it. However, in quantum correlations, according to the Copenhagen interpretation, the particles are in a superposition of states. In English, this means that particles do not have a definite position. And how on earth is that possible? Well, think about how waves behave. Unlike matter, they can be in many places at the same time. Because of this, in quantum mechanics, we say that in the intervals between measurements, particles behave like waves. But be careful, it is not that particles are waves, it's just that they have a certain probability of being found in each place. But this probability oscillates, which means that particles are more likely to be found in some places than in others. However, once a measurement is made, the particle has to choose just one state. This idea can also be applied to pairs of particles. As we have seen, measuring the state of one tells us the state of the other one. So, does this mean that information has been transmitted instantly from one particle to the other? Could we potentially use entangled particles to send information faster than the speed of light? Or even back in time? Well, not quite. And don't worry if you are confused. Einstein was too. He called it spooky action at a distance, because it contradicted completely the basis of his theory of relativity, which states that nothing can travel faster than light. In fact, this was the source of his famous scientific debate with Niels Bohr. Now we know, thanks to Bell test experiments and the violation of Bell's inequalities, that particles do not transmit information faster than the speed of light. In our analogy, there was no communication between the shoes. By looking at the inside of your box, you didn't cause the content of my box, the right shoe, to change. The same thing happens with particles. So sadly, the randomness of the measured results does not let us turn our world into a science fiction novel. However, there is still a lot more to discover. Do we live in Niels Bohr's peekaboo universe, where matter behaves in a completely different way when we are not looking at it? Or was Einstein right, and quantum mechanics is indeed incomplete? Well, both theories can be right, as long as we abandon the idea of particles transmitting information faster than the speed of light. So, magic may not exist, but quantum entanglement does, and it is much more fascinating.